Greetings. We're in the continuing series of finding the electric potential difference between 2 points near a charge geometry, which in this case is an infinite line of charge. So let's get to it. We're going to do this using the definition of potential difference, which you see now written at the top of the screen. dV is negative dot product of electric field dot dl vector. And here we go. Let's see, I need an infinite line of charge. And I'm going to have it go straight across the board. There it is. And I believe it has a charge density lambda. For the sake of argument, we'll say that it is positively charged. And this thing creates an electric field which is directed away from it. So I'll draw a few of these electric field lines. And since I'm drawing the field in the plane of the charge, the drawing doesn't show that the field gets weaker and weaker, but it does as I travel away from the charge. In fact, the expression for this field is E is 1 over 2 pi epsilon naught lambda divided by r, where r is simply the radial distance away from this line of charge. So I want to find the potential difference when I travel from one point A to another point B, which are different distances away from this line of charge. And I'm going to, as I say, this is going to follow fairly closely the same procedure we did for the point charge in the first video. And so this will take less time because I'm going to make use of some of the logical steps we made in that. So here we go. I want to use this, and that means I need to have an expression for the electric field as a vector quantity, and then I'm going to apply that as I walk my curvy path from A to B, in whatever path that I want to. So what is the electric field vector written as a vector? This expression that I have down here is a scalar, which gives me the magnitude of the field. R is the magnitude of the distance from the from this line of charge to any point, such as point A. And so the way I turn it into a vector is the same way that we did before, and so I'm not going to go into that in a lot of detail. If I have a point, I'm just going to put a point over here, P for the time being, which is a distance r away from the line of charge. The electric field at that point has a magnitude of 1 over 2 pi epsilon naught lambda over r. The direction is in the same direction as the position vector from the line of charge to point P. And so the electric field vector at this point, E vector, is parallel to the position vector. So what I will do is introduce a unit vector, r hat, which I've just added to the end of the electric field. I've now turned this into a vector equation. And that unit vector is this position vector divided by its magnitude. The unit vector has a magnitude of 1. I'm drawing it off to the side so you can see it. R hat, it has a magnitude of 1, not 1 meter, but just 1. And it simply gives me, it defines the direction pointing straight away from this line of charge. So now I have this expression for electric field, which is now a vector equation. It gives me the correct direction. So I'm going to go back to this expression over here and make it a vector and put the unit vector at the end. And now I can write the dV, expression for dV is negative that stuff, 1 over 2 pi epsilon naught lambda over r times r hat dot dl. And similar to last time, dl, of course, stands for one of the tiny steps that I take. So now I'm looking at this green path from point A to point B. One of the steps that I take getting from A to B is from here to there. I'm going to magnify it. The displacement change in position from one of those points to the next is this dl vector. And the r unit vector, I'm not going to draw the electric field vector, I'm going to draw the r unit vector at that same point, which points radially away from the infinite line of charge. And the dot product of those two vectors is equal to I'm just going to write this down on the bottom here. The dot product R dot DL, R hat, excuse me, dot DL vector is equal to DR. And if you haven't looked at the earlier video, basically what I'm saying is that the dot product is equal to the component of DL. Here's phi. I'm now looking back up at the diagram where I've taken this little tiny step DL. Here's phi. Okay, the component of DL in the direction of R is going to be purple, and it is, if I make a right triangle here, this distance right here is the component of DL in the direction of R hat, and so that is DL cos phi, and the dot product is the magnitude of R hat, which is 1 times DL, magnitude of DL cos phi, and what that is dr, so I'm going to write, I already wrote this down here, that is the change in length from an R vector drawn to the beginning to an R vector drawn to the end. It's the magnitude and the change in length of those position vectors. It is dr, and it's a scalar, and that's all very nice. So what that means I can do now is get into actually doing the calculation. So I'm going to now write dv, so I'll even go, okay, I'll say delta v is integral dv, which is equal to the integral of this junk, which is negative 1 over 2 pi epsilon naught lambda over r, and this is where I'm going to sub in for the dot product of r dot dl. I'm going to put it sub in dr. So now I have everything written as a scalar, and I can just integrate this bad boy. I'm integrating from RA to RB. These are capital. I don't know why that's important. And so let's see. I will now do this integral. I'm going to pull out the constant. So I've got a negative lambda over 2 pi epsilon naught integral from RA to RB of dr over r. Okay, that's a straightforward integral, luckily. Delta v is, again, negative lambda over 2 pi epsilon naught. And the integral of dr over r is natural log of r. And so I've got natural log of absolute value of r, I believe, but this is, this r stance is always going to be a positive value anyway, because it's simply the distance from the line of charge to the point I'm interested in. So I'm integrating from RA to RB. So that is going to be negative lambda. This is all pretty straightforward stuff at this point, I believe. There's just one interesting thing at the end, so let's just press forward. Natural log of RB minus natural log of RA. I'm going to write that as natural log of quantity RB over RA, using the identity that natural log of B minus natural log of A is natural log of the quotient B over A. And I have this minus sign out here. This is delta V. So I'm going to now write delta V. I'm going to bring the minus sign and distribute it in here. And so I'm going to make use of the identity this time that 2 pi epsilon naught, that the negative of natural log of a quotient is the natural log of the inverse of that quotient. So this now becomes RA over RB is equal to delta V. Okay, let's see, by the way, does this make sense? It's always good to investigate for sign errors. Let's see if this makes sense. In this case, so I'm going to do a make it make sense check. In this case, A is closer to the wire than B is. And so when I go from A to B, am I traveling to a point of higher or lower potential? Well, if I am moving a positive test charge from, I'm going to go purple again for some reason. I'm going to go yellow. I don't know why. So if I'm moving a positive test charge, which is right here, if I'm moving this positive test charge from A along this path to B, I'm moving it in the direction of the electric field, which means that the electric field is going to be doing positive work on it. It's going downstream, if you will, in the electric field. So this thing's going to be losing potential energy. It's going downhill. The electric field is doing positive work on it. So that means that I'm moving from A to B to a point of lower potential. VB is a lower potential than VA. So if I go down here and investigate, does this make sense? My change in potential, delta V, going from A to B should be a decrease, a lower potential. So this should be negative. So let's see, lambda over 2 pi epsilon naught, that's all positive, is natural log of RA over RB a negative value. And let's see, RA is a little number, RB is a big number. So the natural log of little over big means it's a natural log of a decimal, and that means it's going to be negative. And that makes me happy. Delta V should be negative because I'm going to a point of lower potential. So that's nice. That's the difference in potential. The other thing that we did before, you remember with the point charge, is we said that we're going to, this is for point charge, which this isn't. We said that define V equals 0 at R equals infinity. We're not going to do that for this one. And the reason for that is that the difference in potential for a point charge going from any point to infinity is a finite number. So in other words, if you are if you're near a positive point charge, then okay, if here's point A near a positive point charge, the difference in potential between A and infinity is a finite number, like 80 volts. What that truly means is that if I put a positive test charge, where'd my positive test charge go? I don't know why I need the same one, but I do. So if I put a positive test charge, there it is, positive test charge. If I put a positive test charge at point A, this actually is going to be, this should get you thinking about escape velocity, believe it or not, for gravitational fields. If I put this positive test charge at A, let's move the test charge, and release it, it's going to be repelled by this positive charge. It's going to accelerate faster, away from the positive test charge. But it's going to be accelerated by a smaller and smaller force. And when it reaches infinity, it's actually going to be traveling at a finite speed. This is kind of like the opposite of escape velocity for a gravitational field. And that's because this is a repelling force instead of an attractive force. But here's the important point. When I find the velocity of this accelerating charge when it reaches infinity, I'm adding up these changes in velocity that take forever. It's an infinite series, but I'm going to get a finite number for a point charge. What that means then is that the potential difference between infinity and point A, if I bring this back the other way, is a finite number. It only takes us so much energy to bring that charge from infinity to that point. So I can define V0 at R equals infinity. This situation is different. If I have an infinite line of charge, which I can't have because it would take a lot of charge like infinity, there's an interesting contrast here. And we can see it mathematically fairly easily, but it's kind of interesting. If I have this infinite line of, this is positive lambda, and it's truly infinite, which means it doesn't really exist. If I place this positive point charge at point A near this infinite line of charge and release it, okay, it's going to accelerate to the right, just like it accelerated from that positive point charge. And it's going to accelerate forever, just like it accelerated away from the positive point charge. But in this case, as I keep adding these additions in velocity, as this thing accelerates away, and I add up this infinite series of changes in velocity, I actually get infinity. So in this case, now how do I know that? Well, I know that because if I think to myself, all right, let's, as we did before, let's try to define the potential, well, I have it written down here for the point charge. Let's define the potential as 0 at R infinity. If you plug R equals infinity into this natural log function, either for RA or for RB, you don't get a finite value. You don't get 0. You either get positive or negative infinity. And so the change in potential between point A, any point a finite distance away, and infinity is infinity. So we can't say that we can't set the potential as 0 at a distance of infinity the way we do with the point charge. because then it's a useless equation. Then we end up saying, well, the potential at this point then is infinity, and it doesn't help us at all. So that's why it is that we don't do that in this case, and we only have an expression for the change in potential difference between 2 points A and B near a infinitely long line of charge. Whoops, that's my scribble. So we can find the difference in potential between those 2 points, even if there's nothing moving. If I just say what's the difference in potential between A and B, and that's what that expression does for us. And I think I am done. Thank you very much.